To get a better feel for continuity of functions, it's sometimes helpful to look at a few examples. Our first one is f of x equals 1 over x. So if we want to define this, we need to go back and look at the domain. So recall when we're dealing with domains, pretty much the things we have to watch out for are zeros in the denominator, square roots of negative numbers, natural log of 0 or negative numbers. Those are kind of your big gotchas. Everything else is, generally speaking, perfectly fine. So we have 1 over x, so we need to watch out. We can't have 0 in the denominator, so realistically we have to say x is not 0. So everything else but 0 is fine. So we have a discontinuity, well actually we don't know if we have a discontinuity at 0. Well, we know we do. We don't know what type it is. So let's go ahead and just say we have a discontinuity at 0. So if I'm going to draw this, alright, if you go back and remember your families of functions, the 1 over x function, as x gets big, 1 over x gets really small, because dividing by a big number is small. And as x gets really small, 1 over a really small number is a big number. So you have a graph that looks like this. And then the negative, well, it tails out more than that. But in the negative case, it's the same idea, but the values are flipped. So you have this. So you have a discontinuity here at x equals 0. And it's non-removable because there's nothing we can do that's going to make those things work with each other. There's no, like, we can't fill in a hole. We're just out of luck. So the second one is g of x is x squared minus 1 over x minus 1. And if we factor the top and bottom, what we get is that this is close to, I'm going to say approximately x plus 1. The reason why I say that is because we can't just cancel those terms, because if we go back to the original domain, we can't have zeros in the bottom. So we know that x cannot equal 1. So we have a discontinuity at 1. But we say the function is approximately this. So if we plotted a bunch of points, we would get a straight line with that hole there at x equals 1. But if we found a function, specifically that function, and just filled in the hole, well, now we have a removable discontinuity. So we're good. We don't have any issues there. Our next function is a piecewise function. And if you remember what a piecewise function is, it simply is just two different functions put together. We say, alright, for x less than or equal to 0, it's x plus 1. So it looks like this function when x is less than or equal to 0. Now when x is greater than 0, it looks like x squared plus 1. So x plus 1 is just a straight line, slope 1, intercept 1. X squared plus 1 is the standard parabola shifted up 1. So you have something that looks like that. Now the question you're going to say is, alright, what's my domain? Well, in this particular case, there's no problem values here because we're not dividing, or we don't have something where we're dividing by 0 or whatever, and we don't have any square roots. And the same issues here, so our domain is all real numbers, and the function's actually continuous here. So let's say that we had this and we actually plugged in 0. This is the definition greater than 0, but if we plugged in 0, we'd get 1. We plugged in 0 here, we'd get 1. Since those agree, and they're both continuous on their individual domains, then we know that it is a continuous function. So no discontinuities here. Finally, we have y equals sine of x. And if you recall from your study of trigonometry, sine of x is defined everywhere. its domain is all real numbers. This graph looks something like that. It's just a sine wave. It's, this hump is really poorly drawn because they should all be the same height, as is this one here. But ultimately, there's no discontinuities here. Sine function just continuously goes through its period. And generally speaking, this is how you're going to do it. You're just going to take it, look at the domain, take a look at the graph, and that will generally tell you whether or not any discontinuities are going to be removable or non-removable.